Hi, everyone. Welcome back to Econometrics. This is the second lecture of the post-spring break series. So I realized after looking at what I did last time, some of the writing is really hard to read. And so I'm going to try to fix that by writing with a fatter tip on my iPad pen, and then also some of it was cut off, so I'll try to be cognizant of when the computer's cutting it off. If it for some reason still can't get fixed, I will find a workaround, and if you can't understand what I was saying in the last lecture, let me know. All right, we left off on omitted variable bias. Let's pick up there, and yeah, let's talk about what we were talking about. So omitted variable bias, that is when we have a variable that's left out of our regression, that's in the error term UI, contained in the error term UI, and it's also correlated with the included regressor, in this case student-teacher ratios for our example. Something that's contained in UI but correlated with student-teacher ratios, but is also a determinant of test scores. And so the example that we were working with was the percent of English language learners or percent ESL students in the school district. So we have two regressions here that we're looking at, regression 1 and regression 2. Regression 1 has only one regressor, student-teacher ratios. Regression 2 has two regressors, student-teacher ratios and percent EL. So we're going to call PCTEL the percent of English language learners in the school district. So what can we learn from estimating these two models? So suppose these are the two outputs from the models. The first one is the single regressor case. The second is the two regressor case. So we knew, we argued, let's go back and look at what we argued before. We argued that test scores, we argued this little diagram here. We argued the student-teacher ratios are causing a change in test scores. But we also argued that student-teacher ratios are are positively correlated with the percent of ESL students in the classroom. So we're talking about this positive correlation where I have a green arrow pointing to it from last time. We also made the case that the higher fraction of English language learners in a classroom is negatively correlated with test scores. So the negative and the positive correlations multiplied by each other are going to lead to a negative bias in our beta hat 1 coefficient. We know that because we wrote down the equation for bias down here. Let's look at this equation again. Beta hat 1 converges to the true population beta 1 plus the correlation between x and u and their standard deviation. So when the correlation between x and u is negative, then we're going to have negative bias. So let's go back and look at our regression examples that we were working with. Okay, so here we have the sample regressions of test scores on student-teacher ratios, and we get a coefficient of negative 2.28 in the first one. So that means a 1 unit increase in student-teacher ratios is going to reduce test scores on average by 2.28 units. What happens when we control for percent EL in the second equation? We add it to the equation, and that coefficient goes down in magnitude. And so looking at the two, comparing the two, 1.1 to 2.28, or actually negative 1.1 to negative 2.28, we see that there was negative bias indeed in the first regression. Negative in the sense that negative 2.28 is more negative than negative 1.1. So we have we can tell that our estimate here, our estimate in equation 1 of beta hat 1 is biased. We can tell it's biased when we include percent EL in the regression. When we include this in the regression, and we find that the coefficient on student-teacher ratios changes. So here, can we claim that this is unbiased? Not exactly, because there's still an error term. We don't write it because we're dealing with a sample regression, but we could say that there is an error term here. Then there's still stuff included in this error term, like average district income, etc. So this coefficient beta 1 hat still is probably somewhat biased, but it's less biased than it was in equation 1 there. So we haven't established a causal relationship, but we've gotten closer to estimating an unbiased coefficient. Let's see. All right. So we're moving on in lecture note 6. We'll come back to measures of fit for multiple regression a little bit later. Let's look at interactions and marginal effects. I want to get you through enough material that you can do the problem set fairly confidently, and then we'll come back to that. So interactions and marginal effects. Interactions and marginal effects. Okay. A marginal effect is just another way of saying what is the interpretation of beta 1. So marginal effect is the effect of an x variable on y. So when we get to, we expand our discussion from single regressors to multiple regressors, we now think of the coefficient estimates beta hat 1 as marginal effects. Okay, so a marginal effect, suppose our model, let's go up here. Suppose our model is y. I'm going to leave off the i's just to make it easier. Oops, I said I was going to leave off the I. I didn't do it. There we go. The i's are still there, but we're leaving it off. We know the i's are there. Okay, so the marginal effect in this model, this is a standard model of y as a function of x, a single regressor. Okay, the marginal effect, let's say marginal effect is ME. Marginal effect is the derivative, so that's the derivative sign of this function y with respect to x. The marginal effect is dy dx. In this case is going to be beta 1. Fairly simple. So that's the same as what we had before in the single regressor case. Nothing's changed. Now let's say our model. Let's look at a second example. So suppose the model is y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus u. Gotta have our u in there. There we go. What is the marginal effect of x1? Turns out it's the same thing. Just dy dx1, holding x2 constant. That's why we call it controlling for x1 or holding x1, or controlling for x2, holding x2 constant. What's the marginal effect of x2? same thing, beta 2. Okay, not too complicated. Okay, what if we have an interaction? This is a new concept. We haven't introduced this yet. So suppose we have an interaction. What do I mean by an interaction? We have two variables in our model. We have x1 and x2 now. How can we interact them? Okay, so in our data set, we're going to have columns of data. We'll have y, x1, x2, x2. And these are going to be columns with rows on the side, right? So row 1, row 2, row 3, row 4. If y is equal to, these are our values. Suppose this is grid. We have values. I'm making up some values. x2 is 0, 3, 4. I wrote 5 but said 4. Okay, an interaction between x1 and x2 is just going to be simply multiplying the two together. So the interaction of x1 and x2 is going to be this. So we can have an interaction term in our model that's literally just interacting these two variables, multiplying them together. All right, now suppose, let me make some room here. Suppose our model is this. Suppose our model is y as a function of x1, x2, and now the interaction of x1 and x2. What are the marginal effects of x1 and x2 now? We can figure this out. Marginal effect of x1 is dy dx1. Now we're going to hold x2 constant and just take the derivative. It's going to be beta 1 plus beta 3 x2. And what's the marginal effect of x2? dy dx2 equals beta 2 plus beta 3 x1. Oh, that's interesting. So when we have this interaction term, well, let's compare this to what we had before. So without the interaction term, we get a model where the marginal effects are not dependent on the other variable. So the marginal effect of x1 in this model here, marginal effect of x1 is just beta 1. It's not dependent on what's happening in x2. It's conditional on x2, but it's not dependent on it. Okay, suppose the model's this with an interaction term. I forgot to put the u on this. Now our marginal effect depends on x2. Marginal effect of x1 depends on x2. In other words, the effect of x1 depends on the level of x2. This is going to be useful when we start to think about how something like education can affect wages, or how a particular treatment can affect getting your health, or getting sick. Maybe your age is something that affects how the treatment works. So in this case, if x1 is a treatment and x2 is your age, then the marginal effect in this model says that the effect of the treatment depends on your age, which is probably true. So these interaction models can be very useful. Let's look at, all right, I have a lot of room up there. I'm going to start a new whiteboard. All right. What about the interaction of two dummy variables? What's a dummy variable? Let's remind ourselves of that. Interaction of two dummy variables. I'm going to call it two dummy variables. I can barely read dummy. What's a dummy variable? A dummy variable is something that only takes on two values. Just remember that. So one dummy variable example might be whether or not your sex is female or male. Another one might, in this case, be whether or not you have a college. What's our example? Graduated from college or not. So let's suppose we're trying to figure out how education affects earnings. So y, our dependent variable y, is going to be the log of earnings. So that says log earnings. Our dependent variable is that. We'll have one dependent variable, or one independent variable that's a dummy, d1, let's call it d1i, is equal to d1i is equal to, okay, I think I'm figuring this out. 1 if graduated from college, and 0 if not. D2i should be an I. Sorry about that. D2i is 1 if female, and 0 if male. Or we could write otherwise. Our regression function is going to be the following. Suppose we have a regression that looks like this. We're going to assume that's our model. What's the problem with this model? So we're regressing. This model says we think that your earnings or your income is a function of whether or not you graduated from college. Well, that makes sense. We also think that it's a function of your sex, female or male. Now, that kind of makes sense as well, if there's discrimination. The problem, or one problem with this, is that it might be the case that the effect of having a college degree holding, or the problem with this model is that it says that the effect of having a college degree is the same for males and females. Or we're holding gender constant, but we aren't allowing the effect of a college degree to depend on male or female. We might think that the effect of a college degree differs for males and females. So the value of having a college degree might be different for men than it is for women in terms of earnings. So if a man goes and gets a college degree, maybe an engineering or an econ degree, and they go and apply for a job, they might get a higher wage than the equivalent female would. So how can we model this? Well, we can have an interaction. So let's add an interaction. So you should notice that I added beta 3 here which is multiplied by the interaction of d1 and d2. So now these are dummy variables, so we can't really take the derivative of this function to figure out marginal effect. So how do we figure out the effect of a college degree? In other words, changing d1 from 0 to d1 equals 1. How do we figure out the effect of a college degree on earnings? Well, we can compute the conditional expectation for yi given values of d2. So let's do that. Excuse me. So we're going to write the conditional expectation of yi given d1i equals 0 and d2i equals some value d2. So what does this equal? Well, we can take the conditional expectation of this function here and plug in the values. We will get the following. That's a 0 times d2. So that 0 times d2 is going to drop out. We also know by assumption, expectation of ui conditional on d1 and d2 is equal to 0. So the ui is going to drop out. So this bit drops out. So does the error term. And so will that, of course. So then we get that. Okay. What about for D1? What's the conditional expectation for when D1 equals 1? Okay, that's what we get for when D1 is equal to 1. So let's write that out. Okay. So now that we have both conditional expectations, we can figure out the marginal effect, or the effect of a change in college status on earnings. The marginal effect is going to be the difference between the two. The marginal effect equals the difference. I spelled difference wrong. All right, let's take the difference. Expected value of yi, conditional on d1i equals 1, and d2i equals d2, minus expected value yi, conditional on d1i equals 0, d2i equals d2. What does that equal? Well, that equals, subtract these two things so that we can cancel that, cancel that. We get beta 1 plus beta 3 d2. Okay, it turns out that it's the same thing as, did we have that? Nope, that was on the previous slide. It's the same marginal effect. So we could have just taken the derivative, but Since we're dealing with dummy variables, we can't really take the derivative, so we have to take conditional expectations, but in essence, it's the same thing. It's the marginal effect is going to be the coefficient on the variable of interest. In this case, the variable is d1. So we'll have the coefficient here times the coefficient on the interaction term times the variable that it's interacted with. So this says if d1 is education, the marginal effect in this model, the interaction model, the marginal effect is dependent on d2. So the effect of education is dependent on a person's gender. So let's interpret some of these. Interpretation. If person is male, if male, d2 equals 0, the effect of college is beta 1. If female, d2 equals 1, the effect of college is beta 1 plus beta 3. So beta 3 is then the difference in the effect of acquiring a college degree for women versus men. Compare that to the original model where we didn't have the interaction, which said that the effect of a college degree is the same for men and women. In this model with an interaction term, we now see that the effect of a college degree is not the same for men and women. In fact, the difference is beta 3. Okay, what if we have, see where we have room here. What if we have a continuous variable and a dummy variable? Continuous variable and a dummy variable. Okay, consider the model. Consider yi equals beta 0 plus beta 1 xi plus beta 2 d2i. In fact, we don't even need the d2. We can just put di because we only have one dummy variable and one x variable. So yi is again log earnings. So we're trying to figure out the effect of something on earnings. What is that something? So let's say xi equals work experience. In years. So the number of years a person has worked. And di is going to be 1 attended college, 0 no college. How do we interpret this? So beta 2 is again the difference between the intercepts of the two possible regression lines. So really all beta d1 is doing in this, or di in this equation, is adjusting the intercept. So if we forget about xi for a moment, all di is doing is adjusting the intercept beta 0. So when di equals 0, then like we had in our dummy variable example before the break, when di equals 0, beta 2 is really just an adjustment of the intercept beta 0. Or we're getting an average of yi. Beta 0 is the average of yi when di equals 0. When di equals 1, then we add to the intercept beta 2. But suppose we want the effect of additional experience to differ for college versus non-college grads. Suppose we want xi to depend on the effect of, or to depend on a college education. So let's have an interaction model. Let's write that out. Suppose we want the effect of experience to depend on college education, of having it or not. We want the effect of additional experience to depend on having a college education. How can we do this in our model? Well, we have an interaction. So let's adjust our model so that we now have an interaction term. Okay, so now we have an interaction term. It says interaction. This allows for different intercepts and slopes of the regression line depending on whether we are looking at college or non-college grads. In other words, the effect of additional experience now depends on being a college grad or not. And how exactly does it depend on it? So the interpretation is the same as before. Let's say we want to figure out the effect of an additional year of experience. We'll take the marginal effect of the derivative. This is equal to beta 1 plus beta 3 times di. When di equals 0, that's just beta 1. When di equals 1, then it's beta 1 plus beta 3. The difference between the intercepts. Okay, so there's two different cases here. There's the case for college grads and non-college grads. Beta 2 is the difference in intercepts. Beta 1 is marginal effect of experience when D1 equals 0 or no college. Beta 3 is the difference in the effect of experience when someone has a college degree. Oops, not digress, degree. Okay. So beta 1 is an intercept shifter. Sorry, beta 2 is an intercept shifter. And beta 3 is a slope shifter. Okay, let's draw that out. Try to make this clear. Give us some space here. All right, let's suppose we have a model that looks like this. yi equals beta 0 plus beta 1, x1 plus beta 2 d2 plus ui. Now what does it look like when we graph this thing? Okay. Oh, bother. Okay. We're going to get two lines, and it depends. These lines depend on, that's beta 0. The lines depend on what d2 is doing. Oops. Just writing this out first. Okay. So how do we interpret this equation in graph form? So you're going to have to do this on your homework. By the way, the homework tips on how to answer the homework questions for things like this are contained in lecture notes 6, which are posted online. And I will go through that in the subsequent lectures. But let's look at this for a moment. Okay. When d2 is equal to 0 in a basic model with a single continuous regressor, so continuous, and a single continuous regressor and one dummy variable. So one continuous regressor and one dummy variable without an interaction. Then we get two different regression lines that we can plot. The first, the lower one here, has an intercept of beta 0. So when d2 is equal to 0, beta 2 is equal to 0. You can see that beta 2 is going to drop out when d2 is equal to 0 because beta 2 is multiplied by d2. So we're left with beta 0 as our intercept and beta 1 x1 as our slope, or as our regression line. And our slope is always going to be beta 1 because that's the continuous variable. d2 is just an intercept shifter, as we saw before. In this case, b2 is an intercept shifter. So b2 is an intercept shifter. It shifts the intercept. It causes the regression line to go up. So when d2 is equal to 1, then b2 enters the model, and our intercept is going to be beta 0 plus beta 2. However, so we can write our regression model or our expected conditional expectation like that up here, our predicted values. The slope in this case is always the same. The slope is always beta 1. The slope depends only on x1. So that should say beta 1 there. Now let's look at a model where we have an interaction. See how this changes when we have an interaction. Draw the same thing. We're still going to get two lines, but now they look a little different. Now one has a slope of slope of beta 1. And this one has a slope equals beta 1 plus beta 3. Okay. Our intercepts are going to be the same as before. So now beta 2 is still an intercept shifter. But we have beta 3 is a slope shifter. Why is that the case? Okay, let's look at what happens when D1 equals 0. When D1 equals 0, we get a line that looks like this, beta 0 plus beta 1x. D1 equals 0, then the terms in the equation above, beta 2 and beta 3 are going to drop out because they're both multiplied by 0. On the other hand, when when D1 equals 1, then B2 and B3 are left in the model, and we get a regression line that looks like this. Beta 0 plus beta 2, that's our intercept, plus beta 1 plus beta 3 x1. So now, not only does the intercept depend on the dummy variable, but the slope depends on the dummy variable as well. So now, if this were our years of experience and college education example, this would say that somebody with a college education, not only do they have, okay, so let's start with this. So if this is experience, if X is experience, additional year of experience increases your earnings. So not only does experience increase your earnings in both cases, so college degree or not, so this is going to be no college. This is going to be has college. So if you have 0 experience, getting a college degree increases your earnings by beta 2. It increases this difference here. So college with 0 experience is just going to increase your earnings that much. But as you get additional experience, the effect of college on earnings is greater and greater. So the slope here, this slope is steeper than this slope. The slope of the has college line is steeper than the no college line. So people with college degrees, the more experience they get, the more earnings they receive. That's pretty nice if you have a college degree. Now let's look at what if we don't believe this model? What if we think that the effect of more experience is exactly the same, or you start out college, in other words, getting a college degree with no experience has no different, your earnings are exactly the same. So what I'm talking about is right here. What if we think that these two lines should not start at different places? Well, we can model this. Let's write down one last model. So let's say we have a model that looks like this. Okay, what did I leave out of this model? I left out D1 by itself. I left out this term here. I left out D1 by itself. And now I just have X1 in the model and the interaction term. So let's figure out how to plot this. Okay. So now we're going to have two lines that go like this. So we still have our slope shifter. Here's our slope shifter. But we no longer have our intercept shifter. We don't have we don't have D2, beta 2. We don't have D1 by itself, so we don't have our intercept shifter. Okay, what's our slope for this line? Slope for this line is beta 1. So this line is going to be equal to beta 0 plus beta 1 x 1. The slope for this line is going to be beta 1 plus beta 2. And now we can write down, so this is when you have no college. This is when you have college. In other words, here's D1 equals 1, D1 equals 0. All right, now what's the equation for this line? So if we set D1 equal to 1, we still have a beta 2x1 in here. And so we can simplify that a little. Hopefully you can see that. All right, what is our intercept? Our intercept is always now just beta 0. Okay, we have 3 examples. 3 examples. We have one with no interactions. We're always working with one continuous variable and one dummy variable. We know that this dummy variable is always going to be an intercept shifter. So if the dummy variable is included in the model by itself, it's going to be an intercept shifter, this here. And so with a model without an interaction, we're left with 2 parallel lines with different intercept. If we include the interaction but not the intercept shifter by itself, then we're left with 2 lines that are not parallel but start at the same place, the same intercept. And then if we have the model where we include the dummy variable by itself and we have an interaction, then we have not only we have a difference in intercepts, but we also have a difference in the slopes. All right, let's do the easy one. This is the easy one. Interactions between two continuous variables. Interactions between 2 continuous variables. So suppose x1i equals experience and x2i equals years of education. And we have this model. Plus times x2i. So we're going to have, sorry, that's a u. Okay, we're going to have x1 entering linearly, x2 entering linearly, and x1 and x2 interacted with one another. Now, the effect of a change in education depends on the effect of, or depends on the level of experience and vice versa. The effect of experience depends on the level of education. So suppose these are 2 experiences measured in years and education is measured in years as well. In a non-interactive model, if we left out the interaction term, if we left this out, then the 2 would not depend on each other. We would hold them constant, which would be great because we're taking them out of the error term, but we're not accounting for the fact that one can depend on the other. So the effect of one variable does not depend on the level of the other variable. So we can figure out the marginal effects. The difference between the two, or we can figure out the marginal effects of these by taking the derivatives again. So let's figure out the marginal effect. Marginal effect of x1. Marginal effect of 1 is dy dx1 equals beta 1 plus beta 3 x2. In other words, the effect of experience depends on the level of education, and the marginal effect of education, dy dx2, depends on, that should be, depends on the level of experience. Sorry. No. Depends on the level of education. Okay. The marginal effect of education depends on the level of experience. Great. So these graphs are the things that you are going to have to draw for your homework, specifically this one up here. And you can find an example just like your homework in lecture note 6 on page 9. I'll go over that in the next lesson that I'll post probably on Wednesday. And then you can also find how to calculate elasticities using two methods on page 9 as well in lecture note 6. And I'll go through that as well, and that's part of your homework.